Okay, so the guys, the class started. Remember that? Yeah. So the midterm, they'll be graded. I will post the grades on the web page over the weekend once I have them. We expect to finish grading maybe tonight, maybe tomorrow morning, something like that. It takes a little while because, everybody grading has classes and stuff like that, and there's 370 papers to grade. So it takes a little while. I don't know, is anybody, I don't know, do people, so you may have noticed I don't have the computer today, so no clickers today. I know it's breaking your heart, but there it is. Well, so the midterm is what it was. And, okay, so what we did before, what we've done so far, is this business with volumes of, volumes of known cross-section, which is usually surfaces of revolution, but not always. And really the way you do those is you think about what does the cross-section look like, and you integrate it. So, because the idea is that an integral like this is just, this means add up, well, this would be a function. An integral of so if we integrate something, it means add up lots of those guys times some skinny bit. Right? So when we're doing areas, we take a lot of skinny rectangles and they add them up to give us an area. If we're doing, it's easier for me to draw these things this way. If we're doing volumes, then we add up lots of skinny slices, and it gives us a volume. So we can, oops, this isn't what I get to keep. Oh well. We add up lots of skinny things, and it gives us something like a volume, or lots of lines give us an area, and so on. So we can apply this to other ideas as well. So the next idea that I'm going to turn to is, I guess I'll do it over here, is to find the length of a curve. So if I have a piece of rope and it's laid down in some, laid down in some length, and I want to know how long is this rope. Well, the easiest way, of course, if it's a piece of rope or a piece of string, is to just stretch it out and know how long it is. But sometimes you can't do that. If I want to know, I have some curved shape and I want to know how long it is, but it's made out of concrete, it might be a little bit hard for me to just pick it up and measure it. So another thing that you can do is you can chop it up and measure it on segments where it's mostly straight. So that would be, I can measure it on segments where it's mostly straight. I think that's about the same amount. Right? So I can just measure here. So this is 1, 2, 3, 4, 5, 6, 7, 8. So this thing is 8 of those long. So how can we formalize this idea into something that we can use calculus to understand if we know that this length is given by some function? Right? So suppose my question is it clear the question I'm asking? So for example, which I won't do the example first. So, how long is the graph of y equals x squared for x from 1 to 2? So that's the kind of question I want to answer. So if I draw the graph of y equals x squared, well, let's put it over here. Y equals x, that's still a bad graph. I draw the graph of y equals x squared from 1, did I say 1 to 2? Okay. This 2, this is 4, this is 1. Well, that's supposed to be 1, 1. It's a terrible picture. Let's try it again. Y equals x squared. So this is 2, this is height 4. Still bad. 1, 1. It's about right. So how long is this chunk of the graph? So, without doing any calculation, is it bigger than 1? Is it, yes, it's definitely bigger than 1. Is it less than 20? Okay, so at least we have some idea. It's between 1 and 20. Is it less than 5?
Yeah.
Is it less than 4? And now you're starting to get unsure. So what are you doing in order to make these estimates? We have this piece of curve here. I'm trying to guess how long it is. And I know it goes through this point, 1, 1. And I know it goes through this point, 2, 4. And everybody quite easily said that it is longer than 1. Is it longer than 2? Is it longer than 3? So it's somewhere between 3 and 5. So in order to get, so we can estimate this by saying, well, how long is this? It's certainly longer than that. So it's certainly longer than the distance between this point and that point, which is the square root of 1 plus 9, square root 10, which is between 3 and 4. It's certainly bigger than that. And it's certainly less than this, which is 1 plus 3. So it's between square root of 10 and 4. For sure. So suppose I wanted to make my answer better. What would I do? Wait until the professor tells me how to do it. Just one way. What would you do? I'm sorry? No? Okay, what would you integrate? So I haven't worked it up. I just, here's a curve here. And you want to know how long a piece of rope do you need to lay it along that curve? What would you do? You would measure it somehow, right? Take more slopes, sure. So instead of doing this very rough picture, do this rough picture at more points. Go here to here, there to there, there to there, there to there, there to there. That will give you a better answer. And just keep going like that, as much as you want. So I would take this length, this length, this length, this length, and this length, and I would add them up. And that would give me a better answer. And I could just continue in this way. If this answer isn't good enough, this answer is probably, within about that much. If that isn't good enough, do a bunch of really small ones. Do it 100 times. And if that isn't good enough, do it 1,000,000 times. So if I want to measure how long, there's these curves made by the stairs. If I want to know how long these curves are, I could measure it by taking a yardstick and laying them down end to end and adding up however long my yardstick is. I could also take something 1 millimeter long and just lay them down there and go along with 1 millimeter, and that would give me a much better approximation. And if I didn't have a millimeter stick, I could use a nanometer, but I would have to be very patient. So I could get a very good estimate if I go to a very small scale. So that's the idea we're going to use here. So if we have a function, like y equals x squared, this is developed in asymptote, but okay, so we have some function, y equals x squared, and I want to figure out how long this curve is on a very small scale. So I'm going to measure just a little bit. So this is blown up, right? I've blown this way up. Zoomed way in. So this is some tiny amount. dx. That's this distance. This distance is what? dy. All right? For y equals x squared, what's dy? If I tell you dx is 0.03, what is dy for y equals x squared if I tell you that's near x equals, well, it doesn't matter. What do you need to know to calculate dy? Why have you get 0.09? It depends on where x is. My function is y equals x squared. So what is dy if y equals x squared? 2x dx. You guys always forget the dx. The dx is important. It's 2x times this length. Right? If I tell you that this length is 0.03 and the x here is 1.5, then the length of this is 3 times 0.03. Right? dx is a tiny little amount, but it's an amount. You can't just forget it. Okay, so how long is this? How long is the hypotenuse of the right triangle where one side is dx and the other side is 2x dx? What do? I use the Pythagorean theorem, yeah. I used that already. So I'm going to use the Pythagorean theorem. I have a triangle where this side is dx. I keep drawing a, let's make it taller than it is. This side is dx, this side is dy, which in this case is 2x dx. And so this length is this squared plus this squared. Let me just write it as dy squared. Take the square root. Or, in this case where it's 2x dx, this is I can factor the dx squared out. And get that. So that's the length of this. And if dx is really, really tiny, that's very close to the length of that little section of curve. I've done is I've replaced this little section of curve by a straight line. Again, thinking dx is a tiny little number, and that's how long it is. And then we use this idea. We integrate lots of tiny little things, we get a big thing. So that means that the length, so I want to take the limit as dx, well, as the number of, well, okay. So I want to add up lots of these things. And that will give me my length. And I take the limit as the size of the segment goes to 0. So that is an integral. So that will be the integral of this thing. 1 plus 4x squared dx. From, well, let's see, I wanted the curve from 1 to 2, so this is from 1 to 2. This is the length. The graph of y equals x squared between x equals 1, y equals 1, and x equals 2, y equals 4. But I hope it should be clear to you how to do that for any curve. Right, so this is the arc length formula only in this special case. Special case of the curve y equals x squared. We can do this integral by a trig substitution. Right? You all learned that, I hope. Does anyone want me to do this integral? I can do it. Not bad. Use an arc-tan. Yes? No? Does anyone want to see the actual number here? Sure. Why not? You got plenty of time. All right, so if I want to do that integral, I make the substitution x equals, well, so here I really think of this as 1 plus 2x quantity squared, which is what I started with anyway. And I make the substitution that 2x, no, I want to think u is 2x. And so I want the arctan of 2x. I mean the tangent of 2x. What am I doing? U, I want 2x squared. Why is my brain not firing? Because I was up too late last night. All right, so let's just do it in 2 steps because my brain is broken. Du is 2dx. So this becomes 1/2, 1 to 2, square root 1 plus u squared du. Now I make the substitution. U is the tangent of theta. So du is the secant squared of theta. And so this is 1/2, oh. And so u is the tangent of theta when oh, this is not 1, this is now 1/2. This is now 1, right? Because u is 2x, 2 and 4. Okay. Rough day today. Okay, so u is 2 and 4. Now I want to convert that to in terms of theta. So this is the arctan of 2, and this is the arctan of 4. I don't know either of these. Let's see, the arctan of 2 I should know, but the arctan of 4 I don't. So those are some angles. And u is the tangent, so I have a 1 plus a tangent squared, so that's the square root of a secant squared. So that's a secant, square root of a secant theta. So this is 1/2 the log. So I absolutely hate this integral, so it keeps showing up. Secant theta plus tangent theta from arctan, whatever, from arctan 2 to arctan.
Secant squared.
What happened to the secant square for du?
Yeah.
It went away. What do you mean no? Now it's a secant cube because I just forgot it. Because I didn't like it. So now this is a secant cube. And now I don't want to do this anymore. And so on. So there we go. So I'll leave that to you. Okay, so let's do the general idea. Yeah, you can do that on your exam too. You know, you get part way, you write in, so on. I get partial credit. Yeah. Yeah, I get partial credit. Huh? I do? You do? Well, I don't care. I just want to pass. Well, I don't care if I get an A. I'm happy with a C. It's okay with me. All right. So, you know, you can do that. I don't want to do it now because I'm tired of it. So let's come back to this idea of the arc length. And let's redo this a little more generally. The idea is exactly the same. So I have some graph, y equals f of x, and it goes from here, A, to here, B. And I want to find its length. I want to find the length of the graph of this from x equals A to x equals B. Well, it's exactly the same process. I want to go from here to here. So I do the same trick. I chop it up into a bunch of little segments and add up the length of each of those little segments. If I have a little segment of width dx, then the height of that triangle will be dy, and so the length of that little segment will be the square root of dy squared plus dx squared, which, because it's the graph of y equals f of x, then that means that dy is f prime of x dx. Or, if you prefer, we also know we can rewrite this all in terms of dx, factor the dx out. So that means that dy squared plus dx squared, which is the bit underneath the square root, is going to be, well, dy is f prime of x dx. So this is f prime of x dx squared plus that dx squared that I had before. So I can factor out the dx squared. And so the length of the little bit that I want to integrate is the square root of that. Ah! This board is getting worse. sorry I changed the order. Wrong. 1 plus f prime of x quantity squared dx squared under the radical is a dx. So that's not in the radical. So that means that this is the little thing that I want to add up. This part. The part that goes from one piece of the curve runs away, and then comes back to the next piece. These little lines are that long. So the length of the curve is the integral from where I start to where I end, the square root of 1 plus f prime of x dx. That's the integral I want to do. This is square. This is the arc length. This is the square root of 1 plus the derivative squared. And it just comes from looking at this picture and thinking how long is the hypotenuse of a triangle whose leg is dx and whose other leg is dy. So this is not hard. The only problem with this is almost always these integrals really suck. They're really hard to do. In fact, most of them you can't do directly. You have to do numerically. Because square roots are awful, and when you put a 1 in there, it makes it worse. So about the only one that works is like a function whose derivative is the tangent, or the secant, or something. I mean, there are very few examples where these things come out to be nice integrals. They're still integrals, and they still represent something, but you have to do them numerically almost always. A few times, there are a few examples that work out. That's one of them. And let me do one that doesn't work out. This is, let's make it even to 2. This is really easy to write down the integral, but then the integral is not really easy to do. So here we have to find, so f prime of x is 2e to the 2x. That's easy, because my graph is y equals e to the x. Here it is. And I want it to go from 0 to 2. I want the piece of this curve. And so the length and just, for notational, well, okay. Let me just point this out. Sometimes this differential here, this is called ds. So sometimes you might encounter, like in a physics class or something like that, they ask you to integrate something ds. Almost always people use, just like usually, people use x to represent the horizontal coordinate and y for the vertical coordinate. Typically people use s for arc length coordinate. And so in a number of applications, like in physics and so on, you want to have something described in terms of arc length. And so often they will use ds to represent the arc length differential. So, and usually this length of a curve is called arc length. On the side there. So the arc length here is just this integral. I want to go from where I start to where I end, square root of 1 plus the derivative squared, 4e to the 4x dx. Now I can't do anything with that integral. Well, actually, can I? Let's see. If I let u be 1 plus 4e to the 4x, actually maybe I can do this one. Can I? x. So, no, I can't do this one anymore. Square root of e to the u over u. I don't think I do. Doesn't help. So this is one. You know, it's just ugly. So now if you want to know this number, you can use Simpson's rule or something like that. Let me do one that does work out, I guess. So there's like 3 that work out. This is one, but I don't like it. So I have the curve y equals the log of the secant. And let's go from, I don't know, 0 to pi over 4. Some curve, and it has the nice property, let's call it f of x, that f prime of x is 1 over the secant times the derivative of the secant which is just the tangent. And so that means that the arc length here is the integral from 0 to pi over 4 of what? The square root. Okay, that's a good start. 1 plus tangent squared dx. Well, that's one I can do. 1 plus tangent squared is the secant squared, and square root is the secant. The integral of the secant is the log of the secant. And I want to evaluate it from 0 to pi over 4. So the secant pi over 4 is 1 over the cosine of pi over 4. Cosine of pi over 4 is 1 over the root of 1 over root 2. So this is the log of root 2. Secant of pi over 4 is root 2. Tangent of pi over 4 is 1 minus the log. Secant of 0 is 1. Tangent of 0 is 0. Log of 1 is 0. So this is the log of 1 plus the square root of 2. So it's a number. It's about log of 2 and 2. It's a little bit, it's the log of 2. It's a little bit less than 1. The other example that works is, x to the 2/3 power. So let me point out that sometimes these curves are easier to do integrating dy. Remember, the formula is dy squared plus dx squared. Sometimes it's easier if you lay on your side and find dy and factor that out. Let me not do that example. So arc length is really easy, but a lot of students, okay. The idea of arc length, I think, is very easy. This formula makes perfect sense if you think about it. Just draw the picture, you think about it. Most of the stuff in this class, if you just think about it in the right way, is pretty easy. But the integrals are generally horrible. But okay. Computers can do integrals pretty well. Yeah, this one can be done. Not by me, not by me. So what is it? Can you do it? I'm sorry. Tan theta. Oh, yeah, okay.
And then later on, we also have to use the partial fraction in the end.
did too much of this junk already. So I'm happy to just write blah, blah, blah. So I can ask my computer to do these things a lot better than I can do them. So computers are really good at this junk. I have to show you how to do them so you get some sense of what works and what doesn't work. But almost nobody actually does integrals by hand. You have to understand how they work so that you can set them up. But very few people, in calculus classes, actually do nasty integrals like this. You get a nasty integral like this, you ask your computer, it tells you, yeah, that's the answer, or it tells you, I don't know, and then you say, okay, tell me numerically, and it gives it, give me it to 1,000 decimal places, and it gives it to you 1,000 decimal places. So, so any questions on our code? No? Everybody's good with it? Does everyone feel confident that no matter what function I give you, you can set up an integral, not necessarily do the integral, but set up an integral to calculate its arc length? Anybody unconfident about that? Great. Okay, so the unconfident people, those are the people in these empty seats here. People who said, I had an exam last night, I can't get up 9:30, come on. Okay, so let me move on. So arc length is easy. So let's move to the next topic, which is also easy. So it may seem like I'm going fast, but it's easy. So we should go fast when we can, because we're behind. So the next idea, suppose I have 10 numbers, 3, 5, let's do 4 numbers, 7 and 18. These are people's grades on the midterm. And I want to average them. What do I do? Should I be more generous? Okay, 30, 150, 170, and 180. There. These are 4 people's grades on the midterm. What is their average? What do I do to find their average? I add them all up and I divide by however many I have. So this is 30 plus 150 plus 170 plus 180 over 4. Okay. Suppose instead of having 4 grades, I have 400 grades that I want to average. What do I do? I add them all up and I divide by 400. Suppose that instead of 400, I want to compute the GPAs of all students at Stony Brook. What do? I add up all their grades and I divide by however many grades I have. So I'm dividing now by, well, typically people get, say, 5 grades a semester. There's roughly 20,000 Stony Brook students, so I add them all up and I divide by 100,000. Okay, suppose I have some function that describes to me all the grades. And it's not a bell curve because, well, let's make it real quick. So, here is all of the grades. Some people low, some people high, and I want to average it. What do? I add them all up, and I divide by how many I have. So the average is however many I have times sum of all values. This should start to look like something else you know. I add up a bunch of stuff. And I divide by how many, well, other than the dividing by how many stuffs I have, what is this? This is an integral. That means that if the number of things I have becomes very large, so large that we'll call it infinite, you can make sense of the notion of the average value of infinitely many things, or the average value of a function. If I give you some range of values that the function takes on, and I want to figure out the typical value, or the average value, well, let's just do it in terms of a picture for a minute. Here's my function. It's a line. It starts here. It goes here. And I want to figure out what's the average value of all the numbers in between. Well, geometrically, this is pretty easy. I can cut this in the middle. So the average value is just the area divided by the width. In this case, find the area under the curve and divide by its width. That would give me, this is the same, I should have brought a color, oh well, as if I take a rectangle of the average height. In other words, if I take this piece and I cut it off and I flop it down there, there's a point here where the average is achieved. Do people follow this? You're looking really lonely, some of you. Okay, so the average is just the area divided by the width. Well, what's the area? It's the integral. Divided by its width. This is just the exact generalization of that. Add up infinitely many little heights. Divide by how many little heights you have. Exactly the same thing. Why is this useful? Well, this is very useful in things like probability. In probability, you want to talk about the mean, where you sample from a continuous distribution. The mean is just a way of saying the average. Calculate the mean of something that's continuous. You just integrate over the range of possible values and you divide by how wide that is. In a lot of applications, you want to average some function. This is very straightforward. You just find the area, you divide by the width. That gives you the average. In terms of geometrically what we're talking about, another way to say it, we look at the graph. So here's my function. From there to there. I want to find a rectangle who has the same area as this and the same base. So I'm going to cut some off the top and fill in the valley. So I'm just going to take a big bulldozer. Imagine this is a mountain. And this is a hillside, and I want to make it level because I'm going to build a shopping mall there. So I just cut this off and throw it down in the hole. It's not enough, so I cut this off and I throw it down in the hole. And I just smooth this out here. And so this is my average value. It's this height. There's as much stuff above as there is stuff below. It's just the idea of I cut the top off and I fill in the valley. And I make a rectangle of that height. The rectangle of the height, the same width, is the average value. So that means it's exactly this idea. Now, do you need to see an example of this? I mean, it just seems so obvious that it's hardly worth mentioning. But so one fact that is useful in several applications is this mean value theorem. so it's mathematically useful. It says that if I have a nice function that goes from here to there, there's always a point that takes on the average value. Right? So this is the mean value theorem, mean in the sense of average, not mean in the sense of not nice. It says that if I have a continuous function, so this looks like a nice curve. And there's something in between. So there's some C. Is this not, you don't like this? There's a C with C between A and B, so that the value of the function is the same as the average value. This isn't true if my function isn't continuous. If I have a jump, then this isn't true, because right, suppose I have a function that looks like this, and then it jumps down here. Well, the area under this, the average value is here. But there's no C that takes on this height because it's always this height or that height. The function is always 10 and 0. There's no value that takes on 5. So this is false if f is not continuous. But if your function is continuous, then everything's great. All right. Yeah, he has the right idea. Why don't we stop here?